This is the start of a mini-series on a simple executive program written for the Plex emulation. A simple pilot was shown in video 16, which just monitored the peripheral states, but this has been lying dormant until recently. My memory was jogged by the previous videos on the program development route, which showed the trig program looping while peripherals were busy. I mentioned that this was an inefficient use of processing power, so this is an ideal chance to look at an alternative approach. With the trig program, there is some scope for pre-calculating the various blob positions during the wait periods, and saving as many results as it can in the time available. But once it's calculated them all, it will just have to revert to waiting again. Now, this is no big deal for a program which has the whole machine to itself, but it's an unlikely scenario with mainframe systems, where computing time, or mill time, was sold by the second. Now, I have to confess to writing some frivolous programs for our development machines while they were idle. A game of Pong and Conway's Game of Life ring a bell, not to mention porting a turns-based version of Star Trek, which was doing the rounds in all the colleges, from Fortran into one of our in-house languages called Staple, and converting it to real-time operation, causing much distraction to the overnight engineers, as was apparent by the number of high-score printouts in the waste bin the following day. But I digress. If you remember those days, add a comment below. In practice, a special control program would be loaded, which would in turn load and run multiple programs or jobs. Any wait time in one job could be exploited by running another job, which didn't need that same peripheral at that point in time. This would keep the CPU doing real work all the time, and customers could be charged accordingly. Now, these control programs have many names: scheduler, supervisor, executive, operating system, and so on. And there are many ways of dividing up the processing between jobs, not necessarily only at peripheral wait points. If a program doesn't use a peripheral, there are no wait points, but it still may be desirable to switch to another job to share the load fairly. There are a few ways of doing this. A common technique nowadays is to use interrupts, which means each job doesn't need to care what else is going on. The control program just interrupts it whenever it feels someone else needs a turn. Now, Plex does not support interrupts, but there are other methods. The one shown here is a cooperative system, where each job is expected to act as a well-behaved citizen and cooperate with the others by relinquishing control of the CPU at frequent intervals. So this is CoPEx, a cooperative PlasMa executive. The jury is still out on the choice of name, but it will do for now. The idea is for each user job to call a yield routine whenever it needs to wait for something, or whenever it's been processing for a sufficient amount of time, whatever that may be. The yield routine belongs to the executive program, so it can resume other jobs which are waiting to run. Now, obviously there will be contention if multiple jobs want to use the same peripheral, so certain restrictions have to be imposed. For example, jobs should not access peripherals directly. They must use executive routines for this, so the executive can control who accesses what at any one time. Now, interestingly, I found the executive had contentions within itself, such as when accessing the opera screen. So this needed splitting into several subjobs or tasks, and meant the scheduling code needed designing a lot earlier than I had planned. Anyway, this is the scheme so far. It may all change, of course, but we'll see how it develops. The jobs are controlled by a job table, and each entry holds the resume address and the stack pointer. Now, this was something I didn't realise. Each job needs its own stack, otherwise it cannot be resumed properly. Now, you could possibly recode each job so it only calls the yield routine when its stack is empty, but this can make the code very convoluted and difficult to follow. Now, I'm learning this as I go along, again one of the points of PlasMa, but gut feel tells me a job's code should really be structured around its function and not changed out of all recognition just to satisfy the executive's demands. So what does yield do? Well, it saves the jobs registers, and I've chosen to use the job stack for this. It also saves the return address and then cycles through the table looking for the next pending job. And if it finds one, it reinstates that job stack, pops the registers and jumps to the resume address. Now, as long as all jobs cooperate, the scheduler will eventually get back round to the original job, so it won't be suspended forever. That's the plan. The executive subjobs are mainly for sharing the opera screen. I wanted a time of day clock, a prompt system for accepting operator commands, and a scrollable journal to log them. I also wanted a printer job to print the journal for audit purposes. Now, the user job handling is still to do. They need to be loaded from peripherals, so I've just preloaded some placeholders for now. The operator prompt mechanism is also an experiment using a table-driven system to make it easier to change. So, enough of the talk. Here's a demo of the code so far, version 1.0. Okay, while it's loading, just a reminder for any builders out there, do not leave out the speaker circuit. Now, these sounds are all part of the nostalgia. I mentioned before that you get to recognise different programs or even different parts of a program from their sounds. This loader must be quite familiar by now. It's a tiny loop of code, but this was a welcome surprise. It's waiting for operator commands from the external QWERTY keyboard, but instead of a do-nothing wait loop, the more complex sound is the job controller, and that just took me right back. Okay, the opera is divided into three: the top for a title and time of day clock, the middle for status information, and the bottom for operator prompts and the journal. And you have to request a prompt by pressing the escape key. And this also acts as a cancel or abort key, and then use single key presses to navigate the prompt. And if it needs a confirmation, press enter. Right, let's request a prompt. Now, all prompts have a self-destruct timer to cancel themselves if you wander off and leave it halfway. I'm not sure if this was done on systems back in the day. My memory is very rusty, but it seems a sensible thing to do for safety, so why not? Now, the system cannot be fully started until it knows the date and time, so the prompter only offers clock prompts at first, starting with the time. So I'll enter the time, hours, minutes, and enter to confirm. Now the prompter lets us put in the date or correct the time if we got it wrong. So I'll enter the date, 17th of February 2024. Okay. And CoPEx can now start. And that momentous occasion was logged on the on-screen journal, and if you heard it, the printer if it's online. And now we have more prompt choices. Most of these are placeholders. There's still lots of work to be done, but I'll just show a few simple ones. Here's the device status. Device status. And this will eventually be similar to the one in video 16. The system prompts include the clock, which you've just seen. So if the clock drifts or you've got it wrong, you can correct it here. I'll enter a new date as an example. So I got it wrong and it should have been the 18th. Okay. And that's logged as well. There are a couple of job commands. J for job. Status. As you'd expect, gives you a list of jobs and their status. The first ones are the executive subjobs and then the user jobs. Now these will be eventually loaded from peripherals, so they're just placeholders for now. The job stacks are static, and this column shows the amount of free stack for tuning the allocated sizes. This column shows which jobs are running, and at the time the display was issued, there were 2 jobs, the prompter and display job status. I'll probably get this to update automatically every few seconds. And finally, just a crude job control command to give the idea. I want to start job 2, say job 2 run. It's logged, and if I do job status, you can see job 2 running. Job 2 stop. And it stopped. And finally, just a couple of things I noticed which show that jobs are really being multitasked. If you press escape while the job status is being displayed, the prompter job is still able to respond. Job status and escape still works. And similarly, if I ask for a device status before a job status is finished, you can see both jobs accessing different parts of the hopper at the same time. Job status, display status. Okay, that's it. It's very primitive at the moment, but there's no denying the thrill of getting an expensive paperweight to come to life. And hopefully more progress to follow. Thanks for watching.